Hello guys, this is Wits Lounge, Learning Made Easy. And in today's video, we're going to be considering an important concept, and that is the qualitative analysis. Now, mind you, this particular study would concentrate on the West African Senior Secondary School certificate that is coming up very soon. So it's like a practical session to help us understand some of the things we are going to see in the hall. Okay, having said this, we'll get into it. In this particular study, whenever you talk about qualitative analysis, in describing qualitative analysis, you're looking at the constituents of substances. And for you to know the constituent of substances, there are certain things you should look out for. There are reagents that once they react, they will produce certain colors or maybe have certain effects. And once you see those things, automatically you understand that this is this substance. So what we're going to be doing in this study is we'll be considering certain tells. When I mean tells, I mean indicators. Once you see this particular thing, just know that it's this particular thing. You get it's quite easy because take for instance, you see a man walking towards you and that man is staggering. When he gets close to you, he has this smell of booze and alcohol. Nobody should tell you. You should automatically know that that guy is probably drunk. You get the point, okay? Or for instance, there's this tell I heard that when a girl likes you, that the girl begins to call you stupid names like idiot and stuff like that. Yeah, it doesn't make sense, but yes, that's a tell that they described as one of the indications for a girl that likes you. But that's not what we're here to discuss. What we're here to discuss are tells to indicate particular substances or constituent of compounds, basically. Okay, having said that, we're going to get into that. Now, I will just be talking or analyzing certain ions and discussing what is used for testing them, and then we'll use pictorial references to help us understand this. Okay, let's get into it. The first thing we are going to be considering are the tests for your cations. Now, the major cations that are going to be tested are lead, zinc, aluminium, iron 2, iron 3, copper, ammonium. These are the major ones we are going to be considering in this particular study. Having said this, we get into it. The two reagents that are used to test for cations are sodium hydroxide, an aqueous solution of sodium hydroxide, and ammonia. So the implication is that once you look at a particular question and you notice that they said add aqueous sodium hydroxide, it implies that you are likely testing for a cation. If you see add ammonia, it implies that you are likely testing for a cation. And what is a cation? A cation is a positively charged ion. It is a positively charged ion. So when you consider a cation, you are looking at an ion that has a positive charge like Na plus, Pb2 plus, Al3 plus. These things are cations basically. Okay, let's get into it. So we are going to be considering how does NaOH affect cations and how does ammonia affect cations. Now, the general principle behind using sodium hydroxide is that when you use sodium hydroxide to react with salts, you produce the insoluble versions of those salts. Yes, because the only soluble hydroxides are sodium hydroxide and potassium hydroxide. Every other hydroxide of metal is insoluble. So when you react sodium hydroxide with any other salt of any other metal, it produces a precipitate. The precipitate means an insoluble salt. The color is what is going to help us understand, and its action when it is in drops and in excess will tell us exactly what we are looking out for. Now, with this thing said, there is one thing I would like to say, that in testing with NaOH, you first add in drops, and after adding in drops, you then add in excess. Now, if you add NaOH in drops, the first thing that happens is that the hydroxide of the corresponding metal will be formed, which will be indicated by the presence of the precipitate. And after that, you add NaOH in excess. Addition of NaOH in excess is to see if it will dissolve or remain. Now, the only substances that will dissolve in excess sodium hydroxide, are amphoteric substances. Amphoteric substances. Amphoteric substances are substances that can react with both acids and base. And what are those amphoteric substances? You have lead, you have zinc, you have aluminium. These are the three amphoteric substances, which implies that once they are produced as precipitates in excess NaOH, they will dissolve. The implication is that every other precipitate does not dissolve. Why? They are not amphoteric. So have this in mind, that any hydroxide of lead, zinc, or aluminium will dissolve. Why will it dissolve? Because it is what? Amphoteric, and that is, it dissolves in excess. So you are seeing that with this now you have cleared some things. So whenever you see a particular reaction and you hear where the precipitate dissolves, you're either suspecting Pb, Zn, or aluminium. Every other precipitate does not dissolve in excess sodium hydroxide. Okay, let's get to work. Now, having said this, we're going to start with the very first one. I will consider the following metals. I would just like to put up um, just a picture that could help us understand this. Okay, so test for cations using sodium hydroxide. Now, the first thing is that anytime you introduce sodium hydroxide in drops to any salt that contains calcium ion, white chalky precipitates will be formed in drops. And after those chalky precipitate is formed in drops, if you add excess of NaOH, it will remain insoluble in excess. Remember, I told you that the only things that dissolve in excess NaOH are amphoteric substances. And what are the amphoteric substances? Pb salt, Pb hydroxide, aluminum hydroxide, or zinc hydroxide. Calcium hydroxide will definitely remain insoluble in excess. So have that in mind. Calcium will form white chalky precipitate, which remains insoluble in excess. And let me show you what I mean when I say a white chalky precipitate. Okay, so if we consider the image we can see on the screen now, if you look at this image now, you will notice that the precipitate is more like chalk dissolved inside water, and that is why it is referred to as chalky. The other thing about chalky is that chalky precipitates usually settle at the bottom after they are formed, as you can see on the image on the left. Basically, that particular precipitate settled at the bottom. That's actually the difference between the chalky and the gelatinous. And have this in mind, you could say chalky, you could also say powdery. These things represent the feature of calcium ion. The second ion we are going to be considering is lead-2 ion. Lead-2 ion, just like calcium, forms white chalky precipitate in drops. But the difference is that because it is amphoteric, it will dissolve in excess NaOH. So have that in mind. If you see a particular reaction and they said to this solution, add NaOH, and then you see that in the observation, I'm treating this like an alternative to practical. In the observation, you notice that you had a white chalky precipitate. Now, white chalky precipitate could indicate calcium 2 plus or could indicate lead 2 plus. How do we now differentiate it? If you add NaOH in excess, the white precipitate will not dissolve if it is calcium, but if it is lead, it will dissolve. Why? Because lead is amphoteric. Amphoteric means that it can react with both acids and base, which means it should dissolve in a base. So have that in mind, that Pb2 plus would dissolve in excess NaOH. However, when it is in drops, it just forms a white chalky precipitate. We go to the next one. I've indicated or shown you what I meant by the chalky precipitate. So we go to number 3. Number 3 is zinc 2 plus and aluminium 3. These two ions would form what we call white gelatinous precipitate. If you remember earlier on in this class, we said that zinc, aluminium, and lead are all amphoteric, which implies that they can dissolve in excess NaOH. So you have that. That zinc and aluminium will form white gelatinous precipitate, and those precipitates will dissolve in excess NaOH. So what do we mean when we say gelatinous? A gelatinous precipitate is more like, the term I like using is hanging precipitate. So if you notice this picture now, you will notice that the precipitate is more or less hanging, unlike the one of that's the chalky precipitate. Let me bring that up. So if you notice the chalky precipitate more or less sinks to the ground or to the base of the beaker. But in the case of the gelatinous precipitate is hanging. So if you want to note or find out what you mean by gelatinous, just look out for the one that is hanging. So you find out that the picture we have here on the screen is the gelatinous precipitate. Why is it gelatinous? Because it is floating. More or less see it like that. That when you consider gelatinous, you're looking at the floating precipitate. Okay, so having said that, this on the right side is the chalky, this on the left side is the gelatinous. I just wanted to emphasize that just to help us understand this better. Okay, so moving ahead, that is what we refer to as the white gelatinous precipitate. So we continue our journey. Now, moving down to the next one, ion 2. Whenever it is ion 2 plus, think about dirty green, and that dirty green is a gelatinous precipitate, which means it is going to be floating or hanging in drops. But when you now put excess NaOH, it will still remain insoluble. I hope we know why. Because ion 2 is not amphoteric, it will not dissolve in excess NaOH. That's why. So you find out that for ion 2, you are considering a dirty green gelatinous precipitate. Okay, now if you look at the picture here, we have two test tubes. The one on the left side is ion 2, the one on the right side is ion 3. The one on the left side is dirty green. If you look at your picture or the picture very well, you notice that it is a dirty green, and that one on the left side is ion 2, while the one on the right side is reddish brown, and that is for ion 3. Both of them will remain insoluble in excess NaOH. So just have that in mind, that when you're considering um the use of NaOH, when you put it in ion 2 salt, you have a dirty green gelatinous precipitate in drops, and that gelatinous precipitate will remain insoluble even in excess. In the case of ion 3, you have a reddish brown gelatinous precipitate in drops, which remains insoluble in excess. Then finally, we come to ammonium ion. Now, ammonium ion actually reacts with, every ammonium salt reacts with a base to form salt, water, and ammonia gas. So just have that in mind, that whenever ammonium ion or an ammonium salt, you introduce NaOH in an ammonium salt, you will not see any reaction, because you will have a reaction with NaOH to produce a soluble salt. So you will not notice the formation of the salt, because the sodium salt that will be formed is soluble. You will not see it. That's why in number 6 you saw shows no visible reaction. It doesn't mean that there's no reaction, it's just that you can't see it with your eye. Now, however, after you would not see that reaction, you would notice that a gas is going to be given off. One of the things that you are going to note is that as that gas is produced, it has a pungent smell. That gas is ammonia. So just have that in mind, that the gas referred to whenever ammonium salt reacts with NaOH, the gas that is produced is ammonia, and it has a pungent smell. Now, if you want to confirm that this is actually ammonia without any doubt, pass that gas through HCl, either the aqueous form or the gaseous HCl, and you find out that what you're going to have is a white dense fumes of ammonium chloride will be produced. So have that in mind, that if you want to test for ammonia gas, pass ammonia gas through HCl and you have white dense fumes of ammonium chloride formed. So you have that. And these are basically the tests that once you consider, you will be able to indicate these ions. Okay, having said that, let's move on to the next one. The second reagent that is used to test for cations is ammonia. The second reagent that is used to test for cations is ammonia. And what do we have for ammonia? Now, in ammonia, you would have that in the case of sodium hydroxide, we were considering the amphoteric substances. And we said that once it is Pb, it is aluminium, or it is zinc, it will dissolve in excess sodium hydroxide. So you have that. Now, whenever you're dealing with lead, aluminium, or zinc, when the precipitate is formed, they dissolve in excess NaOH. Why? Because they are amphoteric. So every other metallic oxide or hydroxide that is precipitated during that particular reaction will not dissolve in excess NaOH, simply because those other ones are not amphoteric. These are the only ones that dissolve in excess. Now, in the case of ammonia, there are only two ions that will dissolve, or two precipitates that will dissolve, and that is Zn2 plus and copper 2 plus. This is simply because they form tetraamine complexes with ammonia, and those tetraamine complexes are soluble. So have that in mind, that the only ones that are soluble in ammonia are zinc and copper. So every other one will not be soluble in excess ammonia. So zinc and copper 2 plus dissolves in excess ammonia. What is the reason? Because they form soluble complexes with, oh, that's complexes with ammonia. So just have that in mind, that initially when the precipitate is formed is as a result of production of the hydroxide. But when you now further add ammonia in excess, the only two ions that can form the soluble complexes with ammonia are zinc 2 plus and copper 2 plus. Okay, let's see what happens here. Now, if we consider these things, it's as if everything is practically the same thing. So Pb2 plus will form white chalky precipitate, and that precipitate will remain insoluble in excess. Now, however, when you consider the others, let's go to the next one. Aluminium forms white gelatinous precipitate in drops, which remains insoluble in excess. The simple reason is this, that aluminium does not form the tetraamine complexes. The only two substances that form tetraamine complexes are zinc and copper, and that is why they are the only ones that are soluble in excess ammonia. So just have that in mind. Okay, so if you are dealing with uh, Pb2 plus, you have a white chalky precipitate which remains insoluble in excess. If you are dealing with uh, um, aluminium 3 plus, you have white gelatinous precipitate, and that white gelatinous precipitate will remain insoluble in excess. Why? It does not form the complexes we talked about. In ammonia test, you are looking at the ability to form complexes. If it doesn't have that ability to form the amine complex, it cannot be dissolved in excess ammonia. Okay, so we'll move on to the next one. Zinc, on the other hand, has the ability to form the amine complex, so which means Zn2 plus, when it forms the white gelatinous precipitate, would dissolve in excess ammonia because it forms the zinc 2 tetraamine complex. Okay, copper would form a light blue gelatinous precipitate initially with ammonia. But when you now add excess of the ammonia, you are now going to have a deep blue solution formed. So I'm going to try to represent that. Okay, so we have two pictures here, as we can see. The one on the left is the first light blue gelatinous precipitate that is formed initially when you introduce ammonia solution in drops. But when you now add it in excess, you have the one on the right. The one on the right is the one that is formed, the deep blue solution that is formed in excess ammonia. So you have that. Initially, you will see something like this particular picture on the left when you introduce aqueous ammonia in drops. This is light blue gelatinous precipitate. But when you now put the ammonia in excess, the copper 2 hydroxide that is formed now reacts with the excess ammonia to form a soluble blue copper 2 solution. So you have that. So that is the light blue on the left and the deep blue solution on the right. So have that in mind. So we go to the next one. Ion 2, ion 3 will just be the same thing as sodium hydroxide, which means ion 2 will form dirty green gelatinous, which remains insoluble. Ion 3 will also form reddish brown gelatinous, which remains insoluble in excess. So these things are our tests for our cations. Now, mind you, it is important for you to note that anytime you are testing with sodium hydroxide is not used for confirmatory tests. I take it again. Sodium hydroxide is not used for confirmatory tests. So, which means that anytime you are dealing with sodium hydroxide, you are not supposed to use the term confirmed. Use the term present, because sodium hydroxide is not used for confirmatory tests. In the case of ammonia, once you are done with your final test using ammonia, you can indicate that it is confirmed that this particular substance is there. Okay, so having said this, we are done with the major tests for your cations. We'll now go to the test for your anions. Now, considering your anions, the anions I'm going to be considering majorly is dependent on the reagents we have and we are expecting in this exam. We have AgNO3. Now, acidified AgNO3, I prefer to use that term. Acidified AgNO3. Acidified AgNO3. This is silver nitrate salt. Now, acidified implies that you need to introduce an acid that's in drops in little quantity as you are adding the silver nitrate The acidified solution implies that you are going to be adding a little bit of an acid. Any acid can serve, but preferably HNO3, as you are reacting the silver nitrate solution. So you have that. So is used to test for halide ions. So how does it work? Chlorine ion will form chlorine ion forms white precipitate. And please, I would advise that you don't do or try to abbreviate the term precipitate. This is the correct way of abbreviating. Small letter, all written in lowercase or small letter, and then you must introduce a full stop. But however, to avoid confusion, just use the normal spelling of precipitate. So chlorine ion forms white precipitate of silver chloride. That is, the white precipitate it forms is silver chloride. You get. Now, this silver chloride, which is the white precipitate of silver chloride, will remain, sorry, this white precipitate of silver chloride after formation will be dissolved in aqueous ammonia. Yes, wrong spelling of aqueous. Okay, so aqueous ammonia. So just have that in mind, that whenever you see AgNO3, just suspect halides. That is chlorine, bromine, or iodine. Just suspect these three things. When they say acidified AgNO3 or acid plus AgNO3, start suspecting a halide. If you see a white precipitate, automatically you will know that this, what is produced in that particular reaction, is chlorine, or what is inside the solution is chlorine ion. Now, in the case where you see a milky precipitate, bromine ion would form or forms milky precipitate of AgBr. So you have that. So Br minus forms milky precipitate of AgBr, which dissolves in aqueous ammonia. So you have that both chlorine ion and bromine ion will dissolve in aqueous ammonia after their precipitates are formed. However, the final guy we are going to consider is iodine. Iodine ion forms yellow precipitate of silver iodide, which remains insoluble in aqueous ammonia. So please just have that in mind, that whenever you see silver nitrate, acidified silver nitrate, acid plus silver nitrate, and then they say add acid plus silver nitrate to the sample. Once you see white precipitate, you have that is chlorine. If you see milky precipitate, it is bromine. If you see yellow precipitate, it is iodine. Remember, chlorine and bromine are soluble in aqueous ammonia. And when you add the aqueous ammonia, you can now say chlorine is confirmed if it was white, and bromine is confirmed if it was milky. However, in the case of iodine, how do you confirm? When it forms a yellow precipitate and the precipitate, which is yellow, does not dissolve, what you simply say is that iodine is confirmed. Okay, we are going to try out questions to help us understand this more, but let's look out for more of the test. Okay, so the next test we are going to be considering is the test for glucose. Test for glucose. So what are we going to do about the test for glucose? It's quite simple. Now, first of all, before we get into the test for glucose, I would like to say this. Glucose is an alkanal. That is why it is referred to as an aldose sugar. And what do we mean by that? It has a terminal carbonyl group. If you consider the structure of glucose, 1, 2, 3, 4, 5, 6, okay? You have OH, H, OH, 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 H, 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 OH, H. Because it has a terminal carbonyl group, it means that this glucose is an aldose sugar. So just have that in mind. So this is the structure of glucose. And because it's an aldose sugar, it can be oxidized, which means once you introduce oxidizing agents to glucose, it is going to react. Now, we are going to just be considering different oxidizing agents that are likely used to test for this particular glucose. And what are they? What are the oxidizing agents that are used? The first one that is used is Fehling reagent. Fehling reagent. So on reacting with glucose, once you add Fehling reagent to a glucose solution and heat it, you are going to have a brick red coloration. Brick red coloration. Brick red coloration. The brick red coloration is an indication that the glucose has been oxidized while the Fehling reagent was reduced. You get what I'm saying? So Fehling reagent basically is a copper salt that is majorly constituting it. So copper 2 was reduced to copper 1. Copper 1 has a brick red color. So basically that. So that's that basically. If it was Fehling reagent and you're testing for glucose, you will have a brick red coloration. Now, when you introduce the second one is Benedict's solution. Benedict's solution or Benedict's reagent. It would also give you a red color because still copper salt, even though they are different solutions. Red in some cases or orange color. So once you add Benedict's and Fehling's reagent to glucose, the color you are likely to have is brick red or just your normal red color. You get what I'm saying? So that's that basically. Now, the other oxidizing agents that can be used to test for glucose is your Tollens reagent. Tollens reagent. Now, Tollens reagent is basically a silver nitrate salt you get, acidified silver nitrate salt. And what happens in Tollens reagent is this: the silver will be reduced from a silver ion to a silver metal, and that silver metal will now paste on the surface of the test tube glass. So have this in mind. Now, when you introduce Tollens reagent to glucose, what happens is there will be a silver coating of the test tube walls. So have that in mind, that once you are dealing with Tollens reagent, if you introduce Tollens reagent to glucose, you have a silver coating, and that is a confirmatory test for glucose. Now, the other oxidizing agent that is used, even though this is not necessarily the best of confirmatory tests, is acidified potassium dichromate. That's heptaoxodichromate 6. Once you do that, the color changes from orange to green. So have that in mind, that when you introduce glucose to Fehling's reagent, brick red; Benedict's solution, red or orange; Tollens reagent, silver coating of the test tube walls; and then if it is acidified K2Cr2O7, which is your potassium dichromate, you have a color change from orange to green. And these are the tests for glucose. Now, the next test I am going to talk about is basically the test for a carbonate salt. The test for a carbonate salt is very simple and very basic. What is it? You simply add an acid, any acid. So add acid. Preferable acids to use are HNO3, dilute HNO3, H2SO4, or HCl. These are preferable acids to use, basically strong acids you get. So add acid to the solution. So once you add an acid to the solution, what are you going to see to indicate CO3? So CO3 2- is indicated by effervescence. So once you have effervescence, what I mean is, if you notice, if you open a Pepsi bottle or a Coke can and you have that sound, that foamy sound, and all those things, that is as a result of the high pressure because of the gases produced. That's what we refer to as the effervescence. So have that in mind, that once you have CO3 2- and you add an acid, you will notice effervescence. The first thing is, it will be indicated by effervescence to give colorless, odorless gas. So the gas that we produce would be colorless and odorless. So colorless and odorless. Now, if we want to confirm, because there are many colorless and odorless gases, hydrogen is colorless and odorless, oxygen is colorless and odorless, and so much more. But how do we confirm that it is from CO3? Now, it will produce a colorless, odorless gas. The gas we are dealing with is CO2. How do we confirm that it is CO2? When you pass it through lime water, the gas turns lime water milky. So the gas produced turns lime water milky. Okay, when I say lime water, I'm talking about calcium hydroxide solution. Okay, so you have that in mind. Now, what do we have here? We have that if I want to test for a carbonate salt, and what I'm used to test for a carbonate salt is an acid. Now, once you have sample plus acid, and you go to the observation, and you notice that in your observation you have a effervescence, which is followed by production of colorless, odorless gas. How do you know it's CO2? When they now say that it turns lime water milky, you now write in your inference, gas is CO2 from CO3 2 minus. So whether you are dealing with CO3 2 minus or the bicarbonate version, which is HCO3, they have the same test basically. So just have that in mind. Now, the next anion that I'm going to talk about is your SO4 2 minus, SO3 2 minus, and S2 minus. The reagent that is used to test these gases is, these anions I meant to say, is barium chloride. So barium chloride is used to indicate the presence of SO4 2 minus, SO3 2 minus, or S2 minus. Now, how does it work? Now, the very first thing you need to know is that barium forms insoluble salts with all of them, which means that they will all precipitate, and the salts they are going to form are white salts. So just have that in mind, because barium is not a transition metal. It's not a transition metal. So just have that in mind. So with that said, let's get to work. So in the test procedure, if BaCl solution is added to sample and white precipitate is formed, comma, once you have that BaCl2 solution is added to a sample, once you see BaCl2, start suspecting SO4 2 minus, SO3 2 minus, and S2 minus. You know, in the earlier study or earlier on, I said once you see AgNO3, you start suspecting halogens. In this case, once you see barium chloride, start suspecting sulfate, sulfite, and sulfide. Sulfate is SO4 2 minus, sulfite is SO3 2 minus, and sulfide is S2 minus. So let's get to work. So if barium is added to the sample and white precipitate is formed, it means that SO4 2 minus, SO3 2 minus, or S2 minus is present. Now, please notice the terminology I use. I did not say SO4 2 minus, SO3 2 minus, and. I said or, which means it's either of these three. So just have that in mind. Any one of these three can be the answer. Now, how do we find out or get a confirmatory test for this? Now, to confirm, you add to confirm, that is to distinguish which of them is actually correct. So to confirm, add hydrochloric acid, HCl, aqueous. So if you add hydrochloric acid, SO3 2 minus and S2 minus will dissolve in HCl. So after adding BaCl and they say add HCl, once you notice that the precipitate dissolves, your answer becomes SO3 2 minus or S2 minus present, basically. Then dealing with the other one, SO4 2 minus, how would you confirm it? SO4 2 minus remains insoluble in HCl aqueous. So just have that in mind. And why it remains insoluble is because in our production of acids, if you look up that study, you will notice that there are three major ways to produce acids: direct combination, your direct combination, dissolution of your acid and hydrides in water, and then your double decomposition reaction. In the double decomposition reaction, a salt of a weaker acid can actually be dissolved in a stronger acid. But the other way around, it can work. That is to say, a salt of a stronger acid cannot be dissolved in uric acid. SO4 2- is a stronger acid than HCl. That's why its salt cannot be dissolved in HCl. Anyway, my point is this. Once you notice BaCl2, suspect 3 ions: SO4 2-, SO3 2-, or S2-. And how do we confirm that it is SO4 2-? If you add HCl and it remains insoluble, the white precipitate remains insoluble, automatically just know that it is SO4 2-. However, if it dissolves, you're suspecting SO3 2- or S2-. Now, before I end this and we get into a question, I just want to give basic tests for gases. So, test for gases. Test for gases. Okay, the first gas, as we know, is CO2. CO2 turns lime water milky. The next gas is hydrogen. Hydrogen has a characteristic pop sound. When you introduce hydrogen gas, introduce a lighter splint to hydrogen gas, H2 gives pop sound. When I mean pop, like the sound, just pop sound. So H2 gives pop sound with lighted splint. And when we say lighted splint is not so complicated. It's just like a wood, just a broken wood or a piece of wood that is on fire. You get what I'm saying? Once you introduce hydrogen gas, it extinguishes the lighted splint with a characteristic pop sound. And I said pop sound is like, I don't know if you heard that, but you know, that sound. That's the pop sound. Okay. Then we go to the next one, which is oxygen. O2 gas rekindles glowing splint. It rekindles glowing splint. So what do I mean by that? A glowing splint is basically a wood that was on fire. However, after putting out the fire, that yellowish light that is still glowing, that's what we refer to as the glowing splint. If you introduce that glowing splint into a particular container with oxygen, the fire starts again. That's what we mean by rekindling. Now, there are two gases that rekindle glowing splints. Dinitrogen 1-oxide also rekindles glowing splint. So how do we differentiate the two? By their smell. This one has no odor. That is, it is odorless. This one has a sweet smell. So you have that. Oxygen gas is odorless, but dinitrogen 1-oxide has a sweet smell, basically. And you have that. Ammonia. How do we test for ammonia? Ammonia gas is tested using HCl. So it forms white dense fumes with HCl. It is also characterized by its choking smell to the pungent smell of ammonia. Okay, then we have H2S gas. Hydrogen sulfide gas is characterized by its rotten egg smell. So it has a rotten egg smell. So imagine a rotten egg. The smell of a rotten egg is actually the smell of H2S gas. However, the reagent that is used to test for H2S is a solution of lead-2 ethanoate. Why? H2S reacts with lead-2 ethanoate to form black precipitate. So forms black precipitate of PBS with lead-2 ethanoate. Okay, so there are so much more, but these are the very important ones that you need to know. Now, with this said, I would like us to try out some questions, and we'll look into those questions, and with those questions, we'll see how your exams are likely to be. Now, remember, this is more or less an alternative to practical type of thing. It's not, you have to perform the reactions in your schools. I am not performing the reaction in this video. It's more like an alternative to practical, which means we are not performing the practical. We just write out things that you need to know, and once you see that, you give us your likely answer. Okay, so let's get to work. In the test side, if you add sample C to distilled water and you filter, and you observe that C dissolves partially, and you have a green residue with a colorless filtrate, The implication of this statement is that C contains two salts. Anytime you have that there is a partial solubility and partial insolubility, that is one, some of the salts dissolve, some do not dissolve, automatically you have that in your inference. You are going to write it is made up of both soluble and insoluble salts. So have that in mind, that basically you have that the inference should be soluble and insoluble salts are present. Soluble and insoluble salts are present. Now, the thing about these soluble and insoluble salts is this: any salt that is colored is likely from a transition metal. You get, so you could emphasize the fact that because the filtrate is colorless, it is not a transition metal, but the residue being green in color indicates that it is a transition metal. Okay, so let's continue. They now said 2 cm cube of the filtrate plus AgNO3. Remember I told you guys that once you see AgNO3, once you see AgNO3, you start suspecting a halogen. Once you see AgNO3, start suspecting a halogen. So they said 2 cm cube of filtrate plus AgNO3 plus ammonia. So let's get to work. In the first part, when you added AgNO3 and you have white precipitate formed, whenever you have white precipitate formed, we say that it is chlorine ion. If it was milky, we'll say it is bromine ion. If it was yellow, we'll say it is iodine ion. So this white precipitate form implies that our answer is chlorine ion. You get. So let's continue. So you write, how you write it or indicate it is chlorine ion, Cl minus. Cl minus present. You have not confirmed yet. What you used to confirm is ammonia. Now, if you look at it now, they now said AgNO3 plus NH3 aqueous. Now, they said in the observation that the precipitate dissolves in ammonia. Once the precipitate dissolves and it was white before, it implicates or implies that chlorine ion is confirmed. So if you have white precipitate with AgNO3 which dissolves in ammonia, you have confirmed that it is chlorine ion. Okay, moving ahead, we go to the next one. Now, the next one says resulting mixture in B plus excess ammonia. And they now said precipitate dissolves or is soluble. Okay, so you have that. It's more like a repetition of the statement. So we are confirming in this case that it is chlorine, basically. Okay, they now said residue plus HCl, dilute HCl. Now, what comes to your mind? Anytime you see that they said they are adding an acid without anything, you are likely suspecting that a carbonate salt is formed. But before we get to that, let us see the observation. Now, the observation when you add HCl to the residue is residue dissolves to form a blue solution, effervescence. Once you see effervescence, automatically a gas is produced. Effervescence occurs to give colorless, odorless gas evolved that turned blue litmus paper red and turned lime water milky. Once you see lime water milky, there is no need for argument. You are dealing with carbon 2 oxide. Sorry. Once you see turns lime water milky, you are dealing with carbon 4 oxide, which was produced from a carbonate ion. So which means when you get to that particular part, how are you going to represent it? Quite simple. In your answer, you are going to have that it will be written as CO2 gas formed from, or you just write, preferably I would prefer if you write it this way, the gas is CO2 which is formed from carbonate ion. So you write the gas is CO2 formed from CO3 2 minus or HCO3 minus, basically, and you have that as your answer. So whenever you are dealing with that, just have that in mind that that is what you expected to answer. Then finally, they said portion of mixture of C plus ammonia in drops, then in excess. Okay, in drops, then in excess. Very important to note that. So they said that when it was in drops, pale blue, light or pale blue. I told you guys that in ammonia, ammonia and NaOH will have their colors are similar initially, you get. So in ammonia, when you have pale blue precipitate, it is copper. So the first answer is copper. Your first answer is that there is copper there, you get, but you will not write confirmed yet. So this would have Cu2 plus present. Now, they now said that pale blue precipitate in excess, they now said add in excess. So when you add in excess, oh, sorry, in excess was not written. You get, sorry, it was cut off, but then I think it's down. Then in excess. So just have that in mind. They said precipitates in drops of NH3 aqueous to form, wow, my picture is not complete. But what was in that particular question is deep blue solution. So I told you guys that if it was copper, aqueous ammonia will form light blue precipitate that will dissolve to form a deep blue solution. So you have that in mind. Now, with that said, it means that we can now write that copper is confirmed. You can write copper is confirmed because ammonia can be used for confirmatory tests. You get what I'm saying? However, sodium hydroxide is not going to be used for confirmatory tests. So just have that in mind. You can review this study as many times as possible and try to put these things to head. Major things you should note is that when you're using NaOH or ammonia, you are testing for a cation. And in the case of NaOH, it only has lead, zinc, and aluminum as soluble because they are amphoteric, which means they react with base. In the case of ammonia, the only ones that are soluble are the ones that can form the amine complexes, and those are copper and zinc. Basically that. You have that. So with this, I hope this study has been helpful, and I would like to say, keep watching Wits Lounge, where learning is made easy. Don't forget to like and subscribe. Thank you very much.